All right. So yeah, let me tell you a little bit about the alignment and calibration procedure we want to do at LHCb for Run3 in real time. So yeah, of course you have seen our detector a couple of times now, but I still want to briefly tell you about it again, because I will mention all the subcomponents. So we have this detector in the forward direction, where we have the vertex locator around the interaction region. We have the UT before the magnet and the cipher trigger after the magnet to measure the momentum. We have the two ridge stations and the electronic and electronic kilometers for particle identification, and finally the immune stations and to reconstruct and identify muons. So as we've been told several times now, that the Run3 we have this LHCb upgrade detector where we changed a lot of the hardware and are also switching to a fully software-based trigger, which runs at the 30 megahertz non-empty bunch crossing rate. So to get the most out of our detector, we need to reach our precise physics goals. We need to have, of course, the best possible momentum resolution and the best possible PID performance, and of course also the best possible distinction between primary and secondary vertices, since we typically trigger on displaced signatures, and for this we need a very precise alignment and calibration procedure. So just to give an example from Run2 data, you can see on the left the width of the epsilon resonance reconstructed in the unifying states before the alignment left, and then after you run the alignment procedure, you can see that it's much and the width is much smaller. And in addition, we didn't run this offline, but for Run2 already we developed this automatic real-time procedure, which will be even more essential for Run3, as I will tell you. But first, let's go through the alignment and calibration steps and what we need to do here. So what we mean by alignment typically is aligning the tracking systems of the velo, the UT, the cipher, and the immune system, as well as the mirrors of the ridge, which focus the Cherenkov photons. And in addition, we have some calibration steps to calibrate the ridge and the kilometers. So how does the tracking alignment work? So what we do for the tracking systems, it's relatively similar between all of them. So we align the different parts of the tracking system for different degrees of freedom, namely the free translations in X, Y, and Z, and free rotations in X, Y, and Z, as sketched here. And this we do for each alignable element, which are the subcomponents of each detector, are commonly called the alignment constants. So for the tracking detectors, it works like this. So first, we reconstruct tracks with some initial alignment parameters, and those are then fitted with a Kalman filter, and then we use those states from a Kalman filter to get new alignment constants by doing a chi-square minimization, which also allows us to include additional vertex and mass constraints to deal with weak modes. So to briefly write it down, what kind of calculations to do here. So the goal is to minimize this chi-square with respect to the alignment constants, where the chi-square is calculated from the track residuals and the measurement covariance matrix. So if you have some kind of track here hitting a couple of stations or a couple of detector elements, which is described by this track model, which is called here H, which depends on the track parameters, for example, the track slopes. And also here the alignment constants are absorbed here. And then you have your measurements M with some uncertainty as indicated by the spread blobs here, and then the difference between your track model and the measurements. And then so for minimizing this chi-square, you need to calculate the derivatives of the chi-square with respect to alpha and also the second derivatives. And then you can do some kind of Newton-Raphson step where you get a new updated constants using the first and second derivatives. So, and this procedure is performed in several iterations where you need to define some convergence criterion. So what we typically used to have is to require that the change in chi-square divided by all the freedom you have is smaller than 4, and also that the change in delta chi-square for each element or for each alignment degree freedom is smaller than 25. Where this change in delta chi-square depends on the change in the alignment constant and also the covariance matrix of the alignment parameters. So, and if we are not converged after step, of course, then we do it again and we start from construction with the updated set, and then we iterate it until we are converged, hopefully. So going to the value alignment, so this is quite important since the value actually is opening and closing between stable beams. So when the beams are still unstable at the LHC, it's in an open position. Then after they are stable, it's closed, and of course we need to count for this movement since it can misalign our detector. The value consists of those the silicon pixel detector and consists of those 2 halves, which each consist of 26 modules, and each of which consists of 4 sensors. And yeah, this value alignment is really important that we can precisely identify primary and secondary vertices. And as I told you here, we can make also use we can make use of the primary vertex constraints to get a better alignment precision. So one way we can estimate the quality of our alignment of the value detector is to reconstruct PVs using tracks only in one of the 2 halves, so as sketched here on the right. So you just take the tracks just in one half and reconstruct the PVs, and you could take the tracks in the other half and also reconstruct the PVs, and you might get the same PV but slightly different positions for each half. So for example, here in X. And this tells you how well the 2 halves are aligned with respect to each other. So to give you an example, as we studied on simulation where we have a pretty large initial misalignment of the 2 halves, as shown here in those blue points, which shows the difference in the X position of the PVs reconstructed in the left and right halves. And then after you run the alignment, you get a nice distribution around 0, which you want. Another thing we can do to evaluate our expected position of the procedure using some kind of simulated samples using some kind of toy studies where we start with a random non-zero alignment. The input misalignment, which reflects the initial misalignment we expect at the beginning of Run3. And then for each of those samples, we run the alignment until convergence and repeat that for each toy. And we study the distribution of the residual misalignment, where a mean in this distribution it would indicate that our procedure is biased in some way, and the width gives us the precision. So as an example, here on the left, you can see a couple of those toys with some initial input misalignment for the models on the left below have for the TX degree of freedom, and on the right, after you converge your alignment procedure, you can see that the width of the distribution for each model is much smaller and it's unbiased. For the sci-fi, we also started to do some accuracy studies. So as you know, the name tells you, the sci-fi consists of those scintillating fibers, and we need to align it precisely to get a good momentum resolution. And yeah, this sci-fi is quite a huge detector consisting of several modules. And so one thing we started to study this. So what we did is give a couple of modules some initial misalignment in X, as shown on the left, and then we run the alignment, and of course we see then that this misalignment becomes much smaller. Of course, this is only a very preliminary studies, and we probably can do better by use additional mass constraints, for example, from D0 to K pi decays or chip size to mu decays, and also using a larger data sample to improve this precision. Another thing we need to align for are the rich mirrors, which focus those Cherenkov photons. Since if they are misaligned, you get the difference between your measured Cherenkov ring and the ring you expect from your momentum estimate and the intersection of your track with the rich material as sketched here. And this difference is dependent on the azimuthal angle, and this then gives you a distortion as shown here on the top left. And what you can do is to just create the histograms and fit those in each slice of phi to align the rich mirrors, and what you get in the end is this nice distribution, just standard and zero for each slice of phi. And this, of course, is very important to get a good PLT performance. So for the parameters, so we need to calibrate them to account for aging effects, where we have a couple of different steps which provide relative and absolute calibrations, which in the end results in us adjusting the high voltage. So one example is the absolute calibration of the electronic calorimeter using the pi0 to photon case, where we look at the photon merit mass and the pi0 peak there as shown here, and in blue, in red you can see the distribution before calibrating the ecal, which is quite broad, and then you can adjust the high voltages and get a better result of pi0. So now I'm finally coming to the real-time part. So as I told you, for Run2, the LHCb pioneered having an offline-like quality in the online discussion already, which has a couple of nice features, so that we don't need to reprocess our data offline, or don't need to reconstruct things again. And of course, it also reduces then the differences you have in your offline and online version, because they essentially are the same. And just to give you an example, what kind of problems you avoid by doing that. If you look at the efficiency of the value reconstruction during Run1, it was quite different between online here on the left and offline on the right. Of course, this is not, we have a different value for Run3, so it's not, you don't have this issue, but because it's just an illustration of this kind of offline online differences you could have in different parts of your detector, which you want to avoid. So, and for Run3, the real-time alignment is even more important since we are a bit constrained by the bandwidth coming out of our trigger. So it's very important to have very pure selection with less background to reduce our bandwidth. And also a lot of events will actually only be partially safe, which is this turbo approach. So as in this diagram we have already seen, so that we're going through the different readout, trigger, and trigger steps, and then there are a lot of large fraction, so that is this large chunk of top events. We only save partial event information, which means that we can't because the full event offline for those events, and so we need the best alignment and calibration already online for the trigger selection in HTTP2 and HTTP1. So for what we use for the alignment is dedicated events selected by the GPU HTTP1 trigger, which then get put onto this buffer, and we collect events and execute the alignment procedure, and then use the updated constants in HTTP1 and HTTP2, so that we really have this kind of real-time trigger or real-time alignment. To give you some impression of the timescales we had in Run2, so we closed the value and we started, and so you can see in Run2 the value alignment and the tracking alignment was quite fast, just a couple of minutes. Then we had different kinds of calibration steps. So the OT we don't have anymore, but the rich are still similar. And then we had to wait a couple of an hour or two to have enough data collected to be able to align the rich mirrors, and even a bit longer to align the immune system. And finally, at the end, we have enough data to calibrate the colors. So the tracking alignment is finished in a few minutes. So this means we can use actually the updated constants already at HTTP1 if need be. So since we don't use the other detector information for HTTP1, while for example for the rich we need more time, but it's okay since we have on the buffer, and we can then execute HTTP2 with those updated bridge alignments after it's finished. And so the alignment checks if the variation in the constants is actually significant, and only the constants are only updated in the database if they exceed some threshold which we have to define. So for Run2, to give you an impression of the stability of the alignment, here for the value alignment, you can see the variation of the value alignment is over the 2018 run period. You can see the variation in X and Y. And the field points are when we triggered an update, and you can see that we triggered an update quite often due to this opening procedure. For aligning the value, we typically need a sample of around 40,000 minimum bias events, which included proton-proton collisions as well as proton-gas interactions. For the remaining tracking stations, for the upstream and downstream trackers for Run2, and as for the immune system, those were much more stable. So the remaining tracking system we only updated for every couple of weeks using a sample of around 70,000 D0 to kpi decays, and the immune system basically only really moves if you touch it by hand. So, and for that we used 200,000 chip size to immune decays. Now, to put it in the online framework, so the tracking alignment can essentially be split into parts. So one is what we call the analyzer task, which reads in the current constants, then does the track reconstruction using those constants, and calculates the derivatives, so the derivatives of chi-square with respect to those alpha, and writes those to a file. And then the iterator part reads in the derivative file and performs the minimization step, and then writes out new constants and triggers an update if necessary. And so splitting it up like this is nice because the analyzer part can be easily split over different processes or threads. So for example, in Run2, we had a lot of nodes running those analyze tasks, so over different sets of events, and then writing out the derivatives files, and then the iterator collected those, and that did the minimization. And in a similar way, also the rich mirror alignment can be split up, since you have to collect histograms that you can do in different processes. So one of the big differences between Run2 and what we want to do in Run3 is that in Run2 our reconstruction was running using just a single thread. So we had to align, we had to distribute the alignment processes over the whole event filter farm, which is where HT2 was running, which was about 1,600 nodes. And now in Run3, we can make use of this huge speed up we have in the HT2 reconstruction, and also the fact that it's now running with using multiple threads. So we can use fewer nodes, and the current number is about around 160. So you might ask where this number comes from, and actually is related to the number of event builder servers where also our GPUs are placed, if you remember the previous talks. And so this number is still a bit changing. So in some time ago it was 173, now it's 163. And the idea is that for each event building node, you have a dedicated node in the event filter farm, which prioritizes the alignment jobs. So it's very easy to associate the output from HT1 to a specific alignment task. And because of this multi-threading thing, we think that the alignment jobs should take roughly similar time as in Run2, even though we are using less nodes. And finally, this real-time alignment is implemented as a finite state machine, state by the so-called run control. So what we mean by a finite state machine is that we have these processes can have some predefined states, with some transitions between them. And then we have this central run control setting up the jobs and controlling them. So at the beginning, the run control configures and starts the iterator and analyzer jobs. And then the iterator is first idling and waiting for inputs, while the analyzer nodes are starting with reconstruction and calculate the derivatives. Then once those are finished, it tells the iterator to it stops, and the run control initializes a pause transition during which this minimization is triggered. And then either we are converged or not. So if we are not converged, the iterator tells the system to continue, and we start from the beginning. So the analyzer are doing the work again. And if we're converged, then we are stopping and we are finished, and we are updating constants. And that's all I had to say. So yes, we have this fully automated real-time alignment procedure pioneered for Run2, and of course we want to use it also for Run3, where we have quite different environments. So this real-time alignment is quite essential for the best performance, and as I told you, it's essential for our trigger strategy. So it exploits the multi-threaded construction, and currently we are still building up the whole online alignment system. And then of course we have to tune it a bit once we get data and get some feedback from the detector and see how it performs. So thanks a lot for your attention.
Thanks, Florian. Again, let's start with Sue for questions. Okay, somebody, Paolo, you have a question.
Yeah, hi, Florian. Thanks a lot for a nice talk. Just very naive question, because I didn't get it directly, because you said you use some decays to improve the alignment, but I didn't quite catch how this is in within the real time. Do you wait for more data for making the alignment, like the refined alignment using the constraints from the decays, from some specific decays, or is it the luminosity that you get during this prompt alignment, this real-time alignment already enough?
So, of course, for example, for the tracking alignment, we need to collect enough events of a specific decay, for example, D0 to K pi. And we expect this to be very quick because we have a lot of those decays. So in this sense, we are still running real time because it doesn't, for those tasks, it doesn't take a lot of time to collect enough events.
Okay, and just out of curiosity, do you align all the degrees of freedom that you have all in once, or do you have like some staggered, I don't know, different levels of alignment? Just by curiosity.
Yes, I mean, we're still finalizing exactly the configuration, which degrees of freedom to align for and in which order and so on. But in general, so for example, for the velo, we in principle could align down to the sensor level. So, but this we plan to do only at the beginning and then only align the halves and the models in real time. So some of them will be fixed and some of them will be repeatedly aligned for.
All right, thanks.
Are there more questions on Zoom? I don't see any, then let's go to the room. Question in the room? Yes.
Well, then, if I understand, then you run red alignment. Simply you press a button and then let it go. So when the run is finished, the detector is aligned, and then you have everything, all the data processed. That's correct. But then do you do something offline just to improve resolutions or to check if there is some stray features in the data?
I mean, for Run3, you have, of course, to see how the data looks like in the end. And I mean, maybe we need to modify our alignment procedure online, or maybe there's still some tweaks we need to do offline. Like in Run2, for example, we still had some kind of momentum scale calibration, which is not included in the alignment procedure necessarily. Or, for example, can also align using set Boson decays, which is over a larger time scale to collect enough data. So, but I mean, in the end, we really want to avoid rerunning things offline, and it's usually more special cases where you might need to rerun things. It depends a bit on your use case, let's say.
But then I see that, I mean, don't you try this kind of, I guess you have also weak modes, because this is a track-based alignment,
yes.
So you have also weak modes. So there is no cross-check, you are free of that.
I mean, there's some weak modes we are aware of course, because, for example, for the value, we have this planar detectors, so there's some different scaling effects which you would expect, and you can, I mean, there are different ways to account for that and check for that. And I mean, there's also still some weak modes we still need to figure out how to treat them, to be honest. So, I mean, there's still some things we need to figure out.
Okay, on the slide, I see one obvious one. I mean, as yours is quite forward for Atlas standard detector, I mean, aligning the different layers along the beam line, that's quite difficult.
Yes, so that's actually one of the things we are struggling with at the moment. So we are still trying out different things. And yeah, but yeah, that's exactly the thing we are struggling with in this case.
In any case, it looks amazing.
One more. I mean, you showed the effect on the resonance mass pre and post alignment. Are you using this also as a sort of monitoring that you need to do a new alignment, or is the way that invokes running a new alignment run? Is this just given by the fact that you move the velo out the link, or what's the starting procedure?
Not sure I got quite the core of the question, but so I mean, typically, from what I know, I mean that there usually for triggering an update of alignment, we are looking at this this kind of movement here. I mean, there are different conditions, or sometimes also some OR conditions which you can fulfill, and then if one of them is fulfilled, you will trigger an update of the constants. I think probably those like this different resonance masses typically like appear in the data monitoring during data taking, but they are not necessarily used to trigger an alignment.
Okay. Yeah.
Any last question? Any? So let's thank Florian again.